Okay, so this is week 8. Okay, and this week is going to be solving PDEs, and the method that we use, featuring Fourier transform or spectral method. So any questions from the previous session? Okay, then let's start with this one. If you have any questions, just stop me at any point of time. Okay, and ask. So the basic idea, right, is that first of all, any periodic function can be broken down into this Fourier basis, right, e to the power ikx, and then you have coefficients. So the information in phi x is same as information in this f case. So we used phi hat k. Okay, and what's the thing? Well, you can have it as a function of space and time both, right? So it becomes like this, right? And what's the advantage? Advantage is that you can convert PDE into an ODE, and we know how to solve ODEs using various methods, right? RK2, RK4, leapfrog, EAO, everything. And how does this happen? So let's say we're calculating partial derivative with respect to time. So from this, okay, so that will be sum over partial derivative phi k at I kx, and I can take derivative inside, right? So it becomes partial derivative of phi k t e to the power I kx. Now what does this partial derivative mean? It means that x is to be treated as constant, right? As far as this derivative is concerned. So basically you can take this one out or just apply the derivative on this term. Now on that term, that does not depend on x. So we can just write d by dt of phi kt, right? And e to the power I kx. And on left hand side, we have, uh, so this we can write as sum over sum f tilde k t e to the power I k x, right? So what happens is that your partial derivative becomes d by dt, right? So this is the first message. Now second, if you have partial derivative with respect to x, then it is partial derivative. We can expand phi in terms of, so let me just write xt phi kt e to the power I kx, right? And this becomes, now I'll not write all the steps, but phi kt is just constant, right? As far as x is concerned. And the differentiation of this with respect to x is just ik times e to the power ikx. So it just becomes ik times phi kt e to the power ikx. So if you compare these two, we see that del by del x partial with respect to x has the same effect as multiplying by ik to each Fourier coefficient, right? And this is why things become easy. First of all, you get rid of this partial derivative with respect to time, it becomes full derivative, and this partial with respect to x is just vanishes, right? And instead you get one factor. Okay, similarly, if you have double derivative, then you get ik square, right? Which is just minus k square. So this makes our life very easy, and that's the reason why we do this spectral methods, right? So what are the equations that we study? One is diffusion, second is wave, third was Burger, fourth Navier-Stokes, and fifth Schrodinger. Yeah, dot dot. And in all of them, the idea remains same. You have some phi of 0, rather phi of x comma 0 initial, right? And you want to go to phi of x comma t. This is your final, and this is in real space, right? In real space you have some phi of x, and you want to find what happens after time t, but the way you do it is through some diversion. So this is real space. Now go to its Fourier space. This is your Fourier space. So if phi is a function of t, just t, then this will be like frequency space. If it is a function of x, which is the case in all of our equations, then it becomes k space, right? The space of wave vectors. In that, it might look something like this, but then solve it. So here you get phi k of 0, then get phi k of t, which is easy because here there is no PDE, right? Only OD and some multiplications. So you get some other solution, yeah, and then go back to real space, which might be something this. Okay, so and this gives you phi xt. And how do you go from real to Fourier? You do Fourier transform, right? So in NumPy you do np dot fft dot fft, right? And if it is real, then you write R. And this is inverse Fourier transform. So inverse fast Fourier transform. We learned how computers do Fourier transform, right? It's very fast, and that is why we do it. Okay, so I hope this is clear. We go from real space to some abstract imaginary space like dreamland and solve the problem there, and then translate it back to our real physical space. Okay, so in diffusion, I won't go into detail for all of the equations. You have the notes anyways, but the equation for diffusion is del phi by del t is equal to k kappa, yeah, del phi del 2 phi by del x square. Now, by the way, if you don't know how to physically interpret this, generally when you have diffusion equation, you have distribution that is like this, right? The poster boy is always a Gaussian, and the idea is that this shows curvature, right? So here it's positive curvature, here it's negative around the peak, right? And then again it's positive around this region. So and del phi by del t is proportional to curvature. Curvature. So if it's positive here, that means it's going to increase, right? This is the del phi by del t. So it will increase here, it will decrease here because it's negative, and again it will increase here. So after some time, you will get something like this. So all in all, what is happening is that you have something like this, and it diffuses to something like this. Okay, so this is what happens if you have some chemical in water, or even if you are solving random walk problem, then probability distribution itself diffuses, right? So those are the examples. But and in fact, you have some initial Gaussian, let's say to the power minus x square by 2 sigma square, and here you have 2 pi sigma square. Yeah, maybe the coefficient is not correct. Then after some time t, it becomes 2 pi sigma square plus 2 dt or something like that, right? So e to the power minus x square 2 sigma square plus 2 dt, or I don't know, this might be wrong, the coefficients, but with time, what happens is that this standard deviation increases. So the width of the distribution increases. Okay, so that is diffusion. So in Fourier space, we know that del by del t becomes d by dt. So phi k, this is kappa, and second derivative with respect to x becomes minus k square phi k, right? So this is your Fourier, and this can be solved using RK4, RK2, or even analytically, because this is just a simple linear equation. So it becomes I kappa k square. Sorry, there is no I. Phi k 0. This is t. Once you have phi kt, you go back to phi x comma t. Okay. So this is how you solve it. And the second was wave equation. And if you are doing Euler forward, then how will you solve it? So this is like your alpha, right? So every time you multiply phi kn by some factor, that is 1 minus alpha. So kappa k square delta t. And this should be, mod of this should be less than 1 for stability, which means at max this can be minus 1. If this is minus 1, then this term is minus 2. So, sorry, 2. So delta t at max can be 2 by kappa k square for all k. So minimum delta t is less than minimum of all of this, which is 2 divided by kappa maximum of k square, right? So k max square. So this way you can talk about stabilities. So this is a very important result, right? And second equation was wave equation, del t phi is equal to minus c del x phi. Okay. Again, physically what happens for this, I think the best example is something like a triangle. Okay. And so this is phi k of phi of 0, phi x comma 0. So this says is phi tx is equal to minus slope, right? Rather proportional to. So here slope is positive slope. So it will decrease, right? And it will decrease by the same amount everywhere. And here it will increase because the slope is negative, right? So we are assuming C to be positive. So after some time you get something like this. Then you will get something like this. Okay. So what happens is that overall your entire wavefront is progressing and the speed is c. Okay. So if c is negative, then it will go in the left. Okay. And it does not matter what the form is. If you have something like this, then after some time it becomes like this and it just goes on. Right. And you can formally prove it as well, that phi of x comma t is nothing but phi of x minus ct comma 0. So this x is shifted by ct. Okay, so this shift is going to be ct. Okay, in Fourier space, again del by del t becomes d by dt. So d by dt of phi k is equal to minus c, and del by del x gives you I k. Okay, so now your alpha is minus I c k, right? Which means the factor that you multiply is going to be 1 minus I c k delta t, and mod of this is always greater than, because 1 is the real part and you have some imaginary part as well, which means it's not stable, unstable. Does not really matter what delta t you choose, right? If delta t is small, then it will take some time to diverge, but it will eventually diverge. So you cannot solve this using Euler forward. You need to have RK2 at the very least. Okay. And the next third one was the nonlinear equation, which is the Berger equation. And it is like the diffusion equation. This is nu del 2u by del x square. But there is another term, convection, which is del x by del x of u square over 2, or other way to write is u del x u. Okay. And because of this, we get d by dt of uk, right, plus some term due to this, and this term we know it nu times k square uk. Now whatever this term is some non-linear term which we call nk. All right, so we can take this to the other hand. So we have d by dt of uk is equal to minus nk nu k square uk. Okay. And if you look at just the linear part, then your alpha is again nu k square. Yeah. So the factor that you multiply every time, let's call it lambda, that becomes 1 minus nu k square delta t, and mod of lambda should be less than 1, which means again delta t should be 2 by nu k square. Okay. And if you want to do some better methods, then of course this is a linear equation. You can use RK2, RK4, etc. Okay, and there is this Crank-Nicholson, which uses this midpoint method. Okay, so rather than multiplying 1 by nu k square delta t, which is what you do with Euler forward, if you are doing Euler backward, then you divide by 1 plus nu k square delta t, right? Rather than doing both of that, you give half of it here and half of it here. And you can expand this and you can see that up to first order it matches. I think even up to second order it matched. I'm not too sure. So here you go higher order, but for nk just do linear. Sorry, first order. Okay. And then we did fourth one was Navier-Stokes, which is del tu. So now it is a vector, right? U dot del u is equal to minus gradient of p plus nu times delta square u. So you can see the familiar term, right? This was there in all of them. This was the diffusive term. This was there in the Berger equation. Similar to this, not exactly this, right? And this is the gradient of pressure. And then again you can go to Fourier. So what we get is uk d by dt. Yeah. So now this uk itself is a vector. So I can write a vector here or write the ith component, right? I can say x is equal to y, vector x is equal to y, or I can say xi is equal to ya, where I is equal to 1, 2, 3, right? Both are same thing. Then plus, now u dot del will give ik times duk. Is it uk? Yeah. And yeah, there won't be d, right? And then you multiply it with some other index g, right? And then there should be a sum. Yeah, so k itself will be indexed, and then you do sum over j, right? And take the ith component. So yeah, is equal to minus gradient of p. Now gradient is just like del x, right? But for each of the component. So del x gives you ik pk, right? But then you have to take ith component and plus nu times this del square will give you minus k square. So I can make this minus k square uk and ith component. Okay. And the last one was our favorite Schrodinger equation, the time dependent one, right? Del square plus v times psi. So first you can non-dimensionalize this, right? So you can get rid of these ugly numbers sitting in front of that. So you get del by del t psi is equal to minus alpha by 2 gradient square plus v prime psi, right? And alpha is some alpha of all this, right? HM, and the scales, which is RA and EF. This we'll do it later, right? It's one of the assignment question. So again, when you transform it to Fourier basis, you get psi k prime tilde is equal to minus iv prime psi k prime e to the power I alpha by 2 k prime square t prime. Okay. Where this psi tilde itself has some exponential component, which is psi k exponential of I alpha by 2 k prime square t prime. So okay, sorry, there should be d by dt here. So yeah, that was that. Any questions? And one thing about convolution, yeah. So whenever you have multiplication of two numbers in real space, in Fourier space, you get a convolution. So what is convolution? It is sum over fk and g of, so let me make some other number. What, what index can I give? Hij k l, yeah, l, and this is k minus l, and this is summed over l. So as you can see, this total sum total is k. So it is sum over all such components such that total becomes k, and this is your phi k, right? Or you can write f times g at k. Okay. For example, if you want to do fg of 3, then it becomes f3 g0 plus f4 g minus 1, etc. And then f2 g1, f1 g2, f0 g3, f minus 1 g4, etc. Okay, so this is called the convolution. Any questions? Intuitively, you can understand it in terms of probability as well. So let's say x is the number on the dice. So you have one die, okay, and you get 3, and with some probability p3, right? Similarly, it's an unfair, unbiased, rather sorry, biased, right? So if there is probability of getting 1, which is p1, 2 is p2, 3 is p3, 4 is p4, 5 is p5, 6 is p6. Similarly, there is another die which has a different distribution or maybe same, which is q. So 2 has probability q2, etc. 6 has probability of q6. Okay, and obviously sum over pi is 1, sum over qi is also 1, and all of them are qi greater than or equal to 0, pi greater than or equal to 0. Then you ask, so this is your dice x, this is y. Then you ask that what is the probability that x plus y, which is the sum over these two, right? This is what you generally do in most of the games. You roll 2 dice is equal to say 5. So well, you can have 1 on the first die and 4 on the second die. So p1 times q4, or you can have 2 on the first one, 3 on the second one, then 3 on the first one, 2 on the second one, 4 on the first one, and 1 on the second one. So this we can write as p l q4 minus l, right? Where l runs from 1 to, it can go up to p1 to 4, right? Oh, sorry, this should be 5. Total stays 5. Okay, so it's 1 to 4. And if you define all this to be 0, right? P7, P0, etc., then you can just write this as L from minus infinity to infinity, PL Q5 minus L, which is the convolution P star Q at 5. Okay, so this is one way in which you can think about convolution. It's the probability distribution for the sum of the variables. Okay. Any questions, or should we move on to assignments? Okay, let's move on. Let me just check I'm recording. Yeah. Okay, so there are couple of coding questions, maybe three or four, but we'll do the theoretical questions first. So the first one is Schrodinger equation is given, where this is what is the length scale and energy scale after non-dimensionalizing the equation, right? We have probably done this earlier, and what's the idea? Idea is to compare the terms, right? So compare the terms. Let's call this 1, 2, and 3. So let's compare 1 and 2. So you have h square by me, right? We are just looking at the units, and then del square itself has a unit of r square, right? That is important to remember. Remember, del square is like 1 over del by del x square. So this has unit of meters is 1 over r square. And the second term is e square by r, and there was phi here, times phi. Okay, so phi gets cancelled, 1 r gets cancelled, the other side, other r we can send to the other side. So here we have h square by me e square. Okay, where is this? This one, right? And ea is of course same, but we can calculate by comparing 2 and 3. So this becomes your Ra, A for atom. Okay, for 2 and 3 we have E square over R is equal to times phi is equal to E phi. So E is dimension of E square over R. Yeah, not surprising. This is CGS unit, by the way. So EA becomes E square over RA. Okay, and if you substitute this, then you will get the entire expression, which is given in all the four options. So the correct one is the first one. Okay, second one is a coding assignment. Yeah, wave equation is given and all the instructions are given. Okay, so this we'll do later. Let's do the third one. So third one is rather easy if you consider it just as an MCQ. Yeah, what is the correct answer for time scale? And this equation, Schrodinger equation, is given. So we want to know the time, so we can compare first and third one, right? D by dt, so it will be psi over t. Yeah, there is no I has no units, and then m times omega square square times psi. Okay, so psi gets cancelled, and we get t is equal to h by m omega square x square. Okay, now h itself, uh, how should we do it? Yeah, so this x itself has some scale, right? So that we can find using 1 and 2, 2. So h by t is or should we compare? Yeah, let's compare 2 and 3. Okay, 2 and 3. So we get h square divided by 2m 1 by x square is equal to 1 by 2 m omega square x square. Is this correct? Yeah. So we get x to the power 4 is h square by m square omega square. So x is h by m omega square root. This is our xa, right? Maybe I should have give some space here.
Ask,
Yes,
excuse me, can you zoom out it? It's not clearly visible to
zoom
me.
out or zoom in,
Just enlarge it.
enlarge it. Yeah. Okay. Okay. So just to summarize again, first we found the time scale is h divided by m omega square times xa. Okay, scale of x. Now this work we found using by comparing this first term and third term. This is 1 and 3. Now to get x, this was the second. We compare 2 and 3. Yeah, 2 and 3, and the expression that we got was square root of h by omega. So xa is square root of h by m omega. Now plug xa into 1. So this we can call 1. So we get Ta is equal to h divided by m omega square root of h by m omega, which is, oh,
Should be square of xa, maybe. Xa square.
yeah, it's a square. Sorry, square. Thank you. You saved me. So this is square, which is just h divided by m omega square h divided by m omega. So everything gets cancelled except 1 omega. So 1 over omega. And of course, if you have studied physics for a long time, you know that omega is 1 over time. So time scale is 1 over omega, right? So that's the answer. Okay. Fourth one, maybe we can have a poll. You can type out in the chat box which is the most accurate method for solving PDEs. Finite difference, spectral, Laplace, Poisson. We haven't studied the last two, but we have seen finite difference and spectral method. Spectral. Yeah, so everyone seems to be agreeing. By everyone, I mean two people. And yeah, so we had seen that result that h that is needed using finite difference divided by h using spectral method is larger than 1, right? Maybe much larger, I don't know, but it's surely larger than 1. So, sorry, it's smaller than 1. So, basically, you need finer resolution for finite difference than spectral one. So, spectral is better. Okay, and that's why we are doing it. Right. Again. Okay. Fifth one. We have I've told you the answer. Fourier transform of product of two functions. Is it fkgk sum over k fkgk sum over p fk minus p gp or sum over p fk minus p gk? Answer in the chat box. A B C D 1 2 3 4. Yeah, 3 3. Correct. So it's the convolution, right? Mhm. So sum of the indices should be equal to k, right? Which is this index. And this is the convolution. Alright. Can we prove it formally? I haven't tried, but let's see. Fx is sum over fk e to the power ikx. Gx, this is sum over k, sum over k, gk e to the power ikx. So fx times gx is sum over k fk e to the power ikx, then sum over. I cannot use the same k again, right? Because then it means that I should have the same index here and here. So I'll use k prime, or as they are using t, is it going to be p? Let's write k prime. So gk prime e to the power ik prime x. I should zoom in, right? Okay, so this I can write sum over k and k prime fk gk prime e to the power ik plus k prime x. Okay, so even let me not use k, let me use k double prime here. It's dummy index, right? So I can use anything I want. And now I know that this should be equated to k. So k double prime plus k prime is equal to k, which means I can substitute k prime as k minus k double prime. Yeah. So this becomes sum over f of k double prime g of k minus k double prime e to the power ikx, and this is sum over or k double prime, right? Because this is in terms of k double prime itself, and they are just calling this k double prime as p. So it just becomes fp gk minus p e to the power ikx. Is this how they wrote, or is it ulta? Yeah. It's the same thing. You can interchange f and p, right? So f and g. So we can write this as k minus p and gk ikx. Formally, you can write p to k minus p, but still is still from sum is from minus infinity to plus infinity. Okay, and so this is the Fourier coefficient for your f times g and kth Fourier. Okay, sorry, this sum, entire sum. Is this clear? There was some over k which I forgot. So this is sum over k, right? And this we can write as sum over k some fgk e to the power ikx, right? And one thing we know about this Fourier basis is that, well, it is a basis. So if two functions are equal, their coefficients are also equal. Okay, next question. Which of the following is true for Fourier transform fk of a real function fx? Here fk star is conjugate of fk. Fk star is fk, fk star is k times fk, fk star is minus fk, and fk star is minus kfk. Which of them is correct? Answer in the chat box. 1. Let me show the question again. I think this was done in the class, and the correct answer is wrong options. Yes, that's the correct answer. 2. No, 2 is not correct. The closest correct one is this one, but of course it's wrong. It should be f minus k, right? So there is some typo here. Okay. So what this means is that f3 star is going to be not minus f3. Wait, it's real or imaginary? Oh, it's real. Then fk star is f minus k, right? Sorry, not this one. Who said 1? Yeah, Rajesh. Okay, this is going to be f of minus 3. What this means is that in general, let's say you are going from f minus n to f of n, right? Or rather fn minus 1, and there is 0 somewhere, then f1, f minus 1, etc. So you don't really, let me start from minus n plus 1 and go up to fn. You don't really need these terms because the information of this is already contained in these terms. Okay, so if you have in total m terms, then you just need half of the terms plus 1, this endpoint. Okay, this is why when you do real Fourier transform in NumPy, you have half plus 1 as the length of the array. Okay, so should we prove this formally? I think it was done in the class, right? Do you want me to prove it or sketch the proof? Okay, yeah, I think all of you have either done it by yourself or seen in the class. And the next one is calculate this integral using Parseval's theorem and ln 256. So Parseval's theorem I don't think was discussed in the class, but in the current assignment it's given, right? What to do, what is Parseval's theorem? Well, it says that if you calculate the fluctuation of a signal, which is mod xt square dt from minus infinity to infinity, you can either calculate this quantity, which is called the total power or energy, or you can calculate in the Fourier space. So if it is function of time, then you have frequency, right? So x omega square d omega, and probably there is 1 over 2 pi somewhere. This is the way I generally know, but we have function of x, right? And it's discrete. So for discrete one, I think it is sum over fx square dx is sum over fk square. Okay, and then there was some coefficient. We'll see that when we do the problem. Okay, but that's the idea, and this is approximately the integral, right? This is fx square dx. Okay, so this is the idea, and so one thing that we have to find is what is f of x in this problem. So remember, we want this to be fx square. Okay, so this is going to be e to the power minus x square, right? Remember, it's not e to the power minus, sorry, it should be e to the power x to the power 4, not minus x square. Okay, because when you square this, you get e to the power minus 2x square, x to the power 4. Okay, so we'll use this as f. Again, this is Python code, and basically you are given a function which is a function of just x. If you look at left hand side, which is not true, it's a function of y as well, and it has two terms, sin square x and cos cube 2y, and we have to basically decompose it, get the Fourier transform, and look at the amplitudes at kx and ky is equal to 1 and 1. Okay, so this we can do analytically as well. So we know sin x is e to the power I kx minus e to the power minus I kx by 2 square, and cos 2y is going to be e to the power I, by am I writing it? Okay, I 2y plus e to the power minus I 2y divided by 2, and it's going to be q. Okay, so how, what kind of terms will it have? In the first bracket you have x term, right? In the exponent you have 2x term, then minus 2x. I'm forgetting I and everything. Okay, then you have minus 2x and minus 2x. That's it, right? And similarly for this one, and some constant term. And in the second one, you are going to have 2q. So it will have 6y, then minus 6y, then square of this multiplied by this. So 2 times 2, 4, minus 2, which is 2y, and minus 2y, right? And then you have every possible combination of this, and there is order of 1 as well. So 1 2 3 and 1 2 3 4 5, 3 into 5, total 15 terms, right? For example, first term will have e to the power I2x and I6y, but what we want is e to the power I kxx and e to the power I kyy, which is just e to the power ix and e to the power iy, which is not there, right? There are no xy term here, which means the answer should be 0. Okay, so I don't know if you get anything here. We'll see. Maybe there is some error and that gives you one of the answers. But ideally, the answer is 0. So even if it is there, it's going to be very close to 0. Okay. Ninth one. Time stability condition for the Burger equation with Euler forward scheme with time step delta t. Right. So as we saw, the only linear term is this one, and this gives you minus nu k square, and yeah, that's it, right? Minus nu k square. So your lambda is going to be 1 minus nu k square delta t, and mod lambda should be less than 1, which means delta T max is going to be when this is equal to minus 2, right? So, sorry, minus 1. So that will give you 2 divided by nu k square max. So this is going to be your delta T. So this is the maximum value you can take. If you take higher value than this one, then you are screwed. So this is the highest value, so delta T should be less than this, right? And if it is an exam, then I can directly do this because the form of the answer has to be delta T less than something, right? And there is only one such. So, okay, again this one, it's the same thing. Instead of nu, you have kappa, right? And this should be full derivative. So, what should be the answer? I won't ask you. It's the fourth one. Same thing again. Lambda is 1 minus kappa k square delta t, which means delta t max is 2 divided by kappa k square max. Okay. Any questions so far? No? Oh, we have 11 people. So now is a good time to discuss something, and that is that I got message from professor, and he was asking whether you would like to have him in one of the sessions. If you want to ask him some doubts or anything about exams or content, he can be present. So do you want to have a session with him? You can speak up or write in the chat box.
Regarding exams,
Yeah.
actually, I got the email that hall tickets are get released, but link for that hall ticket I didn't get it.
Oh, okay.
So
Who is this? Is this Shilpa?
no, Aparna.
Aparna. Okay. Yeah. So did you write to them? That
I got the mail yesterday, maybe yesterday or day before yesterday.
okay. So you got the mail saying the hall tickets have been released, but you didn't get one.
Huh. They said that there is a link over there will be
Yeah.
provided, and when you click on the link, you get the hall ticket. But I didn't get the mail for such a link email.
Okay. Did others get the link?
No.
No. None of you have gotten. Okay, then probably they will send you soon. If not, then just write to them or even to me. Okay. I hope you have my email ID. I'll type it out in my chat box. To be honest, I really don't know anything about the exam, but I can ask those people. Yeah, and regarding professor, do you want to talk to him, ask something? It's okay. I won't feel bad. Okay, I'm secure about my knowledge. Okay. So since nobody is saying that, I'll just convey this to professor that people are not so interested. Perhaps he did a very fine job in the lectures. All right. And anything else? Yeah.
If we have a doubt, then we can write on your email. Some message will be conveyed to the professor also.
What kind of doubt?
Means any doubt if we have, then we should email to you, and then can you give the same message to the sir?
I can do that, but I have the better option. We have the better option. We can call him on the next meeting, maybe for 15 minutes or something, and you can ask him directly. Isn't it better?
It is on Tuesday or Sunday?
I think Tuesday.
Tuesday.
Is there
Mm.
some issue?
No, not the issue 8, but according to the exam, we just go with all the previous videos, and then if we got something, then I just write over there, and then it will be forwarded. Otherwise, no issue. The lectures and the notes are sufficient for it.
Yeah, okay. So maybe what we can do is have him towards the end of the sessions, like in week 11 or 12, just before the exam. Would it be better?
Yes, sir. Yes,
Yeah,
it's a better. It's a better
yeah,
if after the 12 or maybe in the 11th sessions, if it will have, then it is better because
yeah.
whatever the doubts regarding the exam also, we already done all the things and have the notes regarding that. So it's
Yeah.
better to convey the message.
Okay, then tentatively we will invite him in the 11th week. Okay, you can ask him directly all the questions. Do we, and Rajesh is writing, do we have an option to write the Python program online to find the results in the exam? Yeah, so I asked them and they said that there will be 5 coding questions and there will be some space on the portal or wherever you are writing the exam to write the code and execute. Okay. And again, you this kind of questions you can ask professor. Right. And there was one question in week 6. I think you got the email. So there was no correct option, right? 3.235, yeah, something. So
Yes, for the two assignment we got it.
for 2 assignments, right?
Yeah, for the two assignments. Some I thought week 6 also,
Mm-hmm.
and one more is in there. Revolution. Week 6 and assignment 4 also.
Okay, okay, great. Yeah, so that is solved. And this time assignment is fine, or is there any question with some issue?
Actually, I didn't solve it because that yesterday 2 days we have the lots of function in Maharashtra.
Yeah, yeah, I can understand.
Today,
Yeah,
today I'm going to solve it, and otherwise, so I just request you that just post whatever the discussion happen in here.
yeah.
1 hour after this lecture is get over, up to 9 o'clock at least.
Yeah. So the thing is, if you just want to get by, all of the questions are very easy and you really don't need to code. You can solve it analytically also. If you have just 1 hour, I think it should be doable. And if you have
Now,
just 5 minutes, then you can do at least 6 to 7 questions.
but now that question number 8 you have solved for the 4 year, maybe I don't remember. I took the photo. So that analytical answer we have to calculate. No Python coding is required for it.
Which one?
8 or 7.
This
Not
is
from our assignment. Now you have
from. Yeah, yeah. That I'll do. I'll do using code. I'll code. But in your code, I think in your assignment, some questions are
yes,
from previous years. Yeah.
we
And
have code like same one questions from three four questions from the Python code.
yeah, yeah,
Others are no.
yeah. And this one, for example, is a wave equation, so you know the exact solution. So you can do it using pen and paper like that. Okay.
and, and that question number 10 also, uh, that is
Question 10.
yeah, this one, sorry, hi, yeah, yeah,
Mhm.
Parseval's equation.
Yeah.
So it is not in this week content, so it may be in next week because 9 assignment 9 like videos for the ninth week is already live.
Okay.
So we have the answers regarding this to in there week 9
Okay.
content.
Yeah, but see, they are generous. They knew that it's not covered, but anyways, they wanted to ask, so they have given exactly what to do. And you know how to get the Fourier transform, right? So this should be doable. Nonetheless, I'm going to do a very similar question right now.
Okay.
Okay.
Yes. Thank you.
And I looked at it, and there was one question. I'm surprised that nobody pointed out. In this one, kappa is not given, right? So it looks like nobody has solved it. Or did you assume anything?
This is the problem in the question that is we are facing problem, I think.
Yeah, so this is
Yes.
2024, this year's, yeah. So this
Yes,
second question,
the
I
second
think,
number.
did anyone try this, like, or am I hallucinating? I don't think it can be solved without knowing what kappa is, right?
Yes.
Yeah, so I'll ask them. Anyways, so inside info, if you do kappa is equal to 1, then you get the answer. Okay.
Okay.
Yeah, but it would be unfair to others, those who are not attending, so I'll write to them. Okay. So let's do the coding thing. So the first problem was about the wave equation. Yes, del psi del t is equal to minus 1.5 del psi del x. So speed is 1.5. Solve the PDE in minus pi to pi. Grid points are given. Real part everything. Final time is 5 and x is given, right? And there are few notes. One is use periodic boundary condition, right? We have to, if we are doing Fourier, then it's going to be periodic. Initial distribution has to be given, and it is this one, right? So a Gaussian. Use RK2 for performing integration, and everything is given. Okay, so there is one caveat in this. If you are doing analytically, you have to remember. Okay, so let's look at the equation. So this just means that C is 1.5. That's the only information that is there in this equation, right? And our initial distribution, how would it look like? It looks like a Gaussian, right? And where is it peak? It is at 2, right? So this is x is equal to 2. This is 0 somewhere. And what will be the width of this distribution? So you write this as x minus mu square divided by 2 sigma square, right? So this becomes e to the power minus x minus 2 square divided by this will be 1 by 32, but 2 times 1 by 64, which is just 1 by 8 square. Let me zoom. Okay, so basically your sigma is 1 by 8. So this width is going to be 1 by 4. Okay, so it's a very sharp peak at 2, and this peak is going to move forward with speed 1.5. Okay, so after 1 second it's going to be at 3.5. This is 3.5. This is going to be t is equal to 1. This was when t is equal to 0, etc. But we know that we have a periodic boundary condition from minus pi to pi. So minus pi is 3.14 and pi is going to be 3.14. So when it reaches 3.5, it's actually going to come back here and you will get a peak here. Okay, and then this peak again will move to here and then again go. Once it reaches this boundary pi, it will reappear here. Okay, that's one way to think about it. Other way to think is that you don't have single peak at 2, but rather you have a peak at 2 plus 2 pi, then 2 plus 4 pi, similarly 2 minus 2 pi, 2 minus 4 pi, etc. Okay, and this entire train is moving to the right with 1.5. Okay, so this is going to be 2 pi minus 2, which is 6.28. So minus 4.28. This will be 4 pi. What is 4 pi? 12.56. Yeah, about 12.5. So this will be around minus 10, and this will be 6.28 plus, so 8.28. This is going to be 14.5, something like that. Okay, and now we are asking after what time t is equal to 5 and x is 0.6. So after 5 seconds, this shift is c times t, right, is going to be 1.5 times 5, which is 7.5. Okay, so this peak, which was at minus 10, will move to minus 10 plus 7.5, which is 2.5. This, sorry, minus 2.5. Okay, so it will be somewhere around here, and this will be plus 7.5, so maybe 3 point, what is this? No, 3.2 or something. Yeah, so it will be here, something like this. Okay, so this entire train has moved by this. So, and we are asking what happens at 0. At 0 is somewhere here. And so you need to remember, just because this peak has moved does not mean that at 0 it's going to be close to 0, because there can be a peak somewhere here in the left, right, which can come to 0 and give a non-zero answer. Okay, so now let's do it in the Python. So let's import numpy in matplotlib. Let's write all of the parameters. N is 512, yes, and x is the x array, which is going to be minus pi to pi, right? With how many points? N points. But we don't want the last point, right? So it should be minus n minus pi to pi minus something, such that total number is n. So what we can do is, there are two ways to do it. One is make this n plus 1 and then take only first n. So remove the minus 1. So we are removing the last one. Other way to do is using endpoint. So you say np.linspace from minus pi to pi n, and then just say endpoint is equal to false. So it does not take the last one. But I think this is, it's a desi way, but it's more, you can see it, right? What's happening. Okay. Then C is going to be 1.5, T final is 5. I should zoom in, right? And L, which is the length, is 2 times pi. Dt is 0.01. I don't really need time error, do I? No. And H, the size of one grid, is going to be L divided by N. And I can write the J vector. Anyways, I have defined x, right? So it's not needed. Let's write the function, right? which is the fx. What is the function? Np dot exponential minus 32. I'm writing from here. Minus 32 times x minus 2 square. Okay, this is the initial distribution. Initial condition is t is equal to 0 and fk is going to be. Now we go to Fourier transform. How do we do it? Np dot fft dot fft, but since we are dealing with real, we can use rfft. Okay, real fast Fourier transform of fx, the function, and we have to tell it how many points we have, which is n, and the way we have defined in the course and the way it's defined in Python, we have to divide by n. Okay, so just remember this. Okay, and now we have to define the k vectors, the k array rather, which is the linspace. So I am following more or less the same code that professor showed, right? 0 to n over 2, right? And how many elements are there? N over 2 plus 1. So this double division means we are taking only the integer. So this will be treated as integer. Okay. And let's do one thing. We have to use RK2. Yeah, it's given. But we know that what will be the final answer, right? FKT. It's going to be the exponential of Fk times this exponential. So Fk times exponential np dot exp, and since it's just d by dt, it's going to be minus 1j kt. This is wrong. This times c, right? And then fxt would be the inverse real Fourier transform of this, and now we need to multiply by n. Okay, so this was real to Fourier. Okay, and this is a solution in Fourier. And then we come back to our home, right? The real space. So this is Fourier to real. And then we plot. What should we plot? X and fxt. So let's just see what the solution looks like. Here it's peaked at 0. For this t, it should be t final. T was 0, so it did not do anything. Should be t final. Yeah, now let's run this. Okay, so it's peaked at around minus 3, right? So what is happening is that at 0 it was peaked at 2, right? So let's make t final close to 0, slightly positive. Where is t final? Yeah, let's keep it 0.5. So it should shift to rightwards. Yeah, little bit here. Then let's shift it even more. Let's make it 2. So what happened was it went to the right side and appeared in the left side, right? And then it will keep on doing that. So let's make this 4. You can animate this also, right? I'm not going to do that. And it again shifted to the right. And then we do fifth one. What happens is half of the peak, well, more than half gets to the other side. So right that it appears in the left. So you see this. Okay. So it's peaked at -3 and it continues, right? It goes from left to right, and when it reaches here, magically appears here. That's one way to think. Other is that there are infinitely peaks, yeah, spread equidistant from each other, and the distance between them is 2 pi. So one after the other keeps on appearing. Okay, but we were asked to find its value at 0.06, and to get x is equal to 0.06, we need to round x array up to 2 decimal place. Okay, so let's do it. First, let's round up the array. So x round is np dot round x comma 2. Let's do this in the next cell so that we don't have to run it again in np. Let's find x round. Yeah, so you have just 2 decimal place, and in this we want to find where 0.06 is. Not manually like I'm doing right now, but as you can see there is only one, right? So we want to find where this is, the index of this, and that is done using where. So let's call it the index, and you basically ask np dot where x round is equal to 0.06, and let's print index to see what it is. And it's actually a tuple with one element, which is an array having one element. So if I write 0 here, then it gives the first element of the tuple, which itself is an array. So to get this index itself, I have to write again 0. So I will get 261. And I don't want the index, I want the value at that index, which is ft. What did I call the final function? Fxt. Of index, and it's 0.0. Okay. And why? Because, well, the peak is close to -3, and it's a very narrow peak, right? Just 1 by 4, so just 0.25, and you know Gaussian dies pretty quickly, so it does not have this heavy tail. So it's 0, it's going to be very close to 0. Of course, it can't be exactly 0. So I think it was exponential -12 or something. Okay, so the answer is 0 up to 2 decimal points. Okay, so any questions in this one? We can plot the true solution also, right? So we can say, but we have to shift it by 2 pi. Should we do it? So we can write fxt fx true, which is going to be np dot, this was the original function, right? So it's going to be, instead of x we have minus c times t final. This is the true solution, right? So let's plot this. Oh, in the same way. Yeah, so this orange one is the second one, and as you can see, it's just 0. Can anybody tell me why it is very close to 0, just flat line? The reason is that in calling this as true solution, we did not tell it that it's periodic with period 2 pi, right? So it has just one peak, and that peak is gone, right? It was close to 2, it was centered at 2 at 0. So after 5 seconds, it's going to be at 7.5 plus 2 at 9.5. So that peak is gone, and there was no other peak anywhere. So we have to tell it that it should not be x, but rather a shifted x, right? So we have to define a function shift, and this instead of x, we have to use, instead of this x minus ct, we have to use the shifted one. Okay, rather this should also be included. And how should it be defined? Where should we define? Let's define shift of x. Not all. So one is first try is x mod 2 pi. Okay, but this won't work. Why? Because we want minus pi 2 pi. Right now it will give from 0 to 2 pi, right? If this is higher than 2 pi, if it is 3 pi, then it will just subtract 2 pi. If it is 11 pi, then it gives again 1 pi. Okay, but we want from 0 to 2 pi. So we have to subtract np dot pi. Yeah, but now it gives from minus pi to pi, but now there is an issue. Let's say if it is at 2 pi, then this will give 0 and this will give minus pi. So 2 pi becomes minus pi, but we want it to be pi. So we have to add 1 pi here. Okay, then take the modulo and then subtract that. And this will give the correct shift or folding from the real line to just minus pi to pi. So now let's run this. Yeah, and you can see both of them colors, right? So maybe we can make one of them dashed lines. Oops, I should make the second one dashed one, right? So that the other one is visible. Yeah, now you can see blue and orange, they are collapsing. So what's the message? Well, one is that we can solve it analytically because it's just a wave, right? Other is that whatever we have done is correct. Whatever the parameters, the grid points that we have chosen is sufficient enough to do it. We did not do one thing, which is use RK2, which is what we were asked. So we just wrote direct solution, right? But that is not what was asked in the question. So we have to solve it using RK2. So we do same thing as before. While t is less than t final, uh, first you define k1, which is the slope. So the slope is going to be minus 1j right? Minus I C K. So C times K times Fk, right? This is true. And times dt, of course. So always there. Have I defined dt? Yes. Okay. And if I were doing Rk1, that is the Euler method, then it should be just this, right? Fk plus k1 and t is t plus dt. But we are doing Rk2, so that is going to be what computer tells me. This is correct. Yeah, so it is minus 1j times c times fk plus k1 dt, right? So instead of fk, use fk plus k1 dt. No, it should be just k1, fk plus k1, because k1 itself is dt and we only go halfway, right? So it's going to be k1 by 2 and this multiplied by dt. By the way, here we are doing vector multiplication, right? Rather multiplying array. So k itself is an array, fk is an array. So when we multiply both arrays, Python does it pairwise, right? So index wise. So first component is multiplied with the first component, and that's the first component of k1. Again, second component of k times second component of fk is the second component of k1. Okay, so all these are arrays, and then we are adding. This should be fk plus k2. Okay, and then fkt is going to be just fk, right? Okay, earlier it was this, we directly wrote that. Now we are doing it stepwise using rk2, and finally we get fk. I could have used just fk here, but since I already have fkt here, I'll just say fkt is equal to fk, and let's see if it gives the correct answer. Yeah, it does. I'm surprised I'm not getting enough errors. Anyway, so hopefully you got the idea. Any questions? Okay, and let's look at the next one. Calculate the integral from minus L to L e to the power minus 2x4 using Parseval's theorem, and take L is equal to 4 pi. So it's minus 4 pi to 4 pi and grid size to be 256. Okay, so similar question is there in your exam, your assignment, and in that the process is given, right? And that is that sum over f square x is sum over mod fk square divided by n. So we'll do this, and then integral is this times dx. So dx itself is 8 pi by n. So basically we have to do Fourier transform to get this fk, and then sum it and multiply it by this vector. Okay, so should we define the function first, or yeah, that's this f of x, and that is going to be, so see, it's trying to be smarter, but this is not the function we defined. We define this as the function. Why? Because we want f square x to be this one, right? As we discussed. So this is our function, and let's just write all the parameters. L is going to be 4 times pi, and the grid size is 256, which means this dx is going to be 2 times L, okay, divided by n, right? Don't get fooled by this L being the length. The total length is 2L. It's from minus L to L. So we have 2L by n, and then let's have the X array, which is going to be np dot linspace, yeah, minus L to L, and we don't want the last point, so we do n plus 1 points and then this discard the last point. Okay, and fx is just going to be f of x. This looks very cute, no? And then we do fk. Fk is just going to be np dot fft dot fft of f of x, and then we compute the integral. Let's call it I, and by the Parseval's theorem it's going to be sum of absolute values, right, of fk square, and then we multiply by dx divided by n. That was in the theorem, and print I. Yeah, so this should do, and you get 1.52. Do we have to round up? Yeah, it's not asked. So 1.52, which is there in the problem, hopefully. Yeah, 1.52, the first one. Okay, and the last one, which is the 2D Fourier transform. Okay, so the function is given, and the grid points are given. Let's write the parameters first. 64, and x is linspace from minus pi to pi n plus 1, same thing. And then since we have two things, we need to define mesh grid, which it does. X is in y, and f is going to be sine square x and cos cube y, cos cube 2y. And then the Fourier modes. So we do fk np dot fft, same thing, and now we have to use fft2. Okay, 2D of f, and like by doing when we are doing 1D, we are dividing by n, so we will divide by n times n. This is nx times ny, but nx and ny both are equal to n. And then we need to know kx and ky, right? So we can directly get that using, and it's given in the problem itself, FFT frequency, alright, and then get kx ky as the mesh grid, and what should we calculate? Yeah, fk of 1 1, that is what is asked, and you get 4.03 into exponential of minus 17, so it's very close to 0, which is what we had found. Okay, so it is 0, none of the options is correct. Okay, any questions? Anyone? Kappa is equal to 1 was assumed, yes. Okay, if there are no questions, then let's meet next week. Bye bye.